So this is Stewart Smith. He's a MySQL cluster hacker from MySQL AB. He's an Australian as well, which is kind of cool, and he's been involved with Linux Australia for quite a while now. This talk is going to go to Google Video externally as well, so if you have confidential questions, just wait until we've turned the camera off, please. Cool. So, Stewart Smith.
Thanks, Michael. This is episode 1 of a trilogy of 3 that will no doubt be better than the new Star Wars movies. And the reason it's in 3 parts is because OpenOffice won't let me paste slides into presentations. So I'll start off with a bit of an intro to MySQL Cluster. Do we have any current people who've played with Cluster? Nope. Do you know it exists? Cool. Okay. So you probably already know a bit about MySQL. And in 4.1, we actually added a storage engine called NDB Cluster, which is a high availability clustered storage engine. And in 5.0, we made a whole bunch of improvements to get better speed out of it. And 4.1, it mainly did best at like primary key lookups and index lookups. And in 5.1, we've added even more new features. So you know a bit about how we have storage engines inside MySQL. It's really easy to just have different tables and different types. And there's a bunch of well-known existing ones. And MySQL Cluster is implemented as a storage engine. So you can have some tables in Cluster, some tables in MyISM, some tables in an ODB, all in the same server instance, which is pretty cool. So MySQL Cluster in 4.1 and 5.0 is a in-memory clustered database. So in 4.1 and 5.0, all your data and indexes have to be kept in main memory. But this main memory can be split across several nodes. So if you've got like 10 gig worth of data and you want 2 copies of it, you can have that 10 gig split over 2 machines in 5 gig each, and then another copy of that. And in 5.1, what we've done is added disk data to that, so you can have non-indexed fields stored on disk, but your index is still in main memory. In a future release, we'll also have indexes on disk. We checkpoint the data to disk, so if your whole power goes out on the cluster, all your data isn't lost, you restore to the last checkpoint, which is a nice way of getting your main memory performance when you're committing things, as well as being able to recover from system failure. You can also operate the cluster in a diskless mode, which does no disk I/O. And so if your power goes out, your data's gone unless you dump. So there's a bit of flexibility there. The time between checkpoints is configurable, so you can work out how much data happens there. And you actually have a formula you can apply to work out your disk I/O in megabytes per second. So you can actually grab all your config parameters there and then work out, I need this disk I/O per node. So the rough memory size is this funny little equation of size of database times number of replicas, as in how many copies you want, times about 1.1 due to overhead, divided by the number of data nodes. We design it for high availability, so we have sub-second failover for a storage node failure. We have really quick detection of node failure and fallover. We have a hot backup for the cluster tables, so you type start backup from a management console, and we get just take in the background, dump everything out, and then like have triggers on things and generate logs, which does it pretty quickly and pretty efficiently. And again, the rate that happens is configurable, so you don't have your backup like overwhelming your cluster. And of course, the amount of redundancy you have in the system is configurable as well by an easy number of replicas parameter. We have a shared nothing architecture, so you don't have an expensive storage area network at the back end. You just have a bunch of like commodity machines that communicate via Ethernet. We also have the transporter layer, so the way that nodes communicate with each other is pluggable. So along with using like a TCP transporter layer, you can also get like SCI cards, which is a high performance interconnect that has really takes about 1.4 nanoseconds to do a 4-byte write between nodes on SCI and stuff like that. So you get quite low latency there, which has a big performance improvement for a bunch of apps. So the way the components look in a cluster is at the end we have normal MySQL applications, like using the client library, that talk to normal MySQL servers, so these are spread out across machines. And it just so happens that instead of all these MySQL servers talking to their local disk, they send messages across a wire to a bunch of storage nodes. So we've got a bunch of storage nodes that actually store the data, while the SQL servers sit at the front and then process the SQL and translate to where exactly it has to look up in which data node, that kind of deal. And these data nodes here perform stuff internally, like talk to each other to do the distributed transactions and replicas and stuff you need. So everything here, it is synchronous replication. So that any of these servers, when you do a transaction here, It's synchronously available here. There's no like lag between applying a log or anything like that. Everything here is done synchronously. We also have a management server down the bottom, which is its essential job to distribute the configuration file to say, hi, new storage node, look at these IP addresses for the other nodes. And then you just got a little management client that lets you like start backups, monitor what nodes come in and out. And there's an API, you can do that too. So if you want to have like link into your own monitoring systems, you can do that. So the type of nodes we have inside the cluster is we have a storage node, which is grouped into node groups. And each node group holds a section of the database. So we have internally, you can partition things out as well. So you can have, sort of half your database is in one node group, half of it's in another. And the number of nodes in a node group is how many replicas you have. So your cluster is available as long as you have one node in each node group, as in a complete copy of the database. We have, as I said before, configurable number of nodes in the node group, as in how many replicas you have. We have up to 48 in a cluster, which some people say, what, only 48? But rare do we get like people with transaction loads that actually count up to that don't want to maybe also use replication and stuff. So the traditional market of cluster has been like telcos, doing like telco applications, which have like, small fixed size rows and maybe a lot of them, but really want the HA thing in there. And, their transaction load doesn't get beyond, a few 100,000 transactions per second, which we can quite easily handle. So we can expand it as well. So if you suddenly have a requirement, we actually need a 200 node cluster, that can be expanded with relatively minimal effort on our part, and up to like huge numbers that will get there as well. But there's code that has to be written for that. We have a management node, said just distributes configuration, does a couple of interesting things, but we'll probably get more interesting in the future as we add some features. And we also have a MySQL server node, and you can also program the cluster directly in a C++ API. So if you didn't want to have to go through the MySQL server and have SQL doing everything there, you can actually program direct to a C++ API to say, do a table scan on this table with these conditions and other such things, and get a performance boost out of that because knowing exactly what your application's doing. And you access these just like you would any other MySQL server, because it's just a storage engine from MySQL, right? So it's just really just typing SQL queries as if it was anything else with, obviously a few differences underneath. So physical requirements for setting up a cluster is the node is a process, not a computer. So you need at least 3 machines so you don't have the problem of a split brain and decide who's a cluster. We won't ever let you have 2 clusters that aren't communicating with each other and doing updates on both, because that would be like bad. So we do a whole bunch of like quorum code within to prevent that. Management server doesn't need a powerful machine. Data nodes typically have a lot of memory, especially in 4.1 and 5.0, since we had everything had to be in main memory. And also, of course, caching stuff on disk off disk is a good thing. So in 5.1, when we've got data on disk, it's good to have a whole bunch of memory in there as well, so you can cache more, as well as your indexes still have to fit in main memory. The disk I/O requirements, especially for 4.1 and 5.0, because we have all these lovely configuration parameters in there, you can set limits. And there's a couple of cool equations to get that megabyte per second of how much disk I/O you're ever going to use. They're generally not CPU bound. You have a lot more API nodes, so a lot more MySQL server nodes have to be running queries against the data nodes to get them up to like 100% CPU usage. So you generally need maybe less powerful CPUs there, or less number of nodes than you do processors accessing the cluster. And NDBD, we say, is single-threaded. It has its own internal task switching mechanism, which ends up being a way bit more efficient than doing like context switches in the OS. We have a lot less state transferring. So we actually get a good bit of performance out of our internal architecture there. And if you have several CPUs in a box, run multiple nodes on the one box. That's the easy way to do it. MySQL nodes need the most CPU, as you're doing like query processing, parsing, and doing a whole bunch of extra stuff in there, dealing with results and sending them out. So you can need like maybe bigger boxes or more nodes. More nodes is easier to add, and you can add currently like MySQL server nodes online, so you don't have to bring down the cluster to add new MySQL server nodes accessing the cluster. You can't add data nodes online yet. We're working on that. I can show you a demo patch if you want, but don't expect it yet. Pardon?
Is it going to be possible to add data nodes online later?
Yeah, possible to add data nodes online later. Yes, it will be possible in the future. So we've done some work on that now, and we're now focusing like development work on making sure that the 5.0 and 5.1 releases, especially 5.1 with the new features I'll talk about later, are as bug-free as we can ever make them. And then I'll get back to writing the online add node and add node group stuff. So it's in two passes that online add data node. One is actually get the nodes into the cluster, and the other one is repartition data inside the existing data nodes onto those new nodes. The first phase is relatively simple. The second phase is hugely complex when you start to getting into node failures during rebuilding tables and system failures and stuff. And we want to get that right. I wouldn't run my experimental patch for adding data nodes yet. Cool. So if we look at an example configuration of it, so we have a config file for the cluster. And you can say, as a configurations options here, like number of replicas, we say we want 2 copies of our data in the cluster. And you can set like how many concurrent operations you will allow, the maximum number of concurrent operations. So you don't have this risk of suddenly trying to allocate more memory for like storing operation records and running out and things exploding. You set a maximum, and the storage node processors don't grow. They stay that constant size. So you don't have the problem of like running out of memory and stuff on machines. Predictability is a good thing when you want HA. How much data memory and index memory? Again, predictable sizes. We don't run out, that kind of thing. That also, I believe, is one of the online upgradable parameters. So you can take down a box, add more RAM sticks in it, bring it back up sequentially through your cluster and get more memory in that way. Which directory you actually want to store data in, how many maximum number of indexes and stuff you want in the cluster. And here we have 2 storage nodes in this little one management server. The management server, you can have more than one in there, but you don't need it for continued operation of the cluster. Have it in there, so it doesn't really matter if it goes down. Don't get out of bed, just fix it in the morning. And we have like a MySQL LD server configured here, which you can add more. So we have these 2 storage nodes that have an interconnect between them. If you're worried about like latency and want to get a bit extra performance, like SCI guys can do some cool hardware that isn't too expensive and stuff. Management server, the storage nodes pull configuration out of the management server to find out where each other is and a few other things. And it's also used in arbitration in the case of network splits. So if you lose this connection here, the management server will decide who becomes the cluster. And you can also run MySQL AB on that or another box. And you naturally have sort of the outside world, so your end applications coming through the MySQL servers and talking to the storage nodes. So you want sort of like a private data network down here. So you don't sort of have other apps like chewing up all your network bandwidth and your nodes dropping off. So failure scenarios. A MySQL server node can fail. So you can easily just restart these and they come back into the cluster. Or you notice there at the bottom there, we don't have like IP addresses allocated to MySQL servers. So you just plug in another box and say connect to cluster. Bang, throw the old one out because it's too tricky to reconfigure them, right? And applications can easily reconnect to another MySQL server node. So if they're connected to a MySQL server node, they get the connection terminated. Just go to a list of your other ones and connect it through. A lot of people use software or hardware load balancers between them. So you can do it that way. Storage nodes, when a failure is detected, all other ones are informed about the failure. And since data is replicated, right, we've got number of replicas equals 2, so we'd have 2 copies of the database, or we can have 3 or 4. There is another storage node to service new transactions. And the current implementation is that when a storage node fails, any client applications that are doing transactions involving that storage node, their transactions are aborted, and you have to retry those transactions. But all that should be written that way anyway, in case you get deadlocks and stuff in transactional engines. So in reality, that shouldn't really be a problem. In the future, question?
When you say all the storage nodes are notified, is that storage node in the node group or all storage nodes everywhere?
All storage nodes everywhere are informed of the failure, in case there's any other protocols running between each of the nodes. So did I repeat the question then? Probably not. So the question was, are just the nodes in the node group informed of the failure, or is everyone? And the answer is that all data nodes are informed. There can be other protocols like backup. Like since you've got replicas there, you can do other cool things like backup and other queries and stuff around. So everyone's informed and can take action depending on what's going on at the current time. And the management server node, continued operation of the cluster isn't reliant on the management server being up. and you can also have multiple nodes. And when you have multiple management server nodes, the UI for sharing configuration is make sure your config files are the same on each machine. But in the future, we'll probably fix that up. So you just have to be a bit more careful with more than one. But there's clever guys here. So you actually want to use the cluster after this bit of architecture introduction. It's a storage engine. We don't support foreign keys yet. That's planned for the future as well. And we support the 5.0 features. You can do views on clustered tables, store procedures that access clustered tables, triggers that act on clustered tables, use your standard permissions interface. I say these have to be set up on each SQL server node. So inside the MySQL database, where we store all this stuff, that's my ISM table still. So you can actually have different MySQL servers connected to the cluster with different sets of permissions, which is either a bug or a feature, depending on who you ask. But people, I think, have experimented with replication and stuff to do this, or using replication to get it the same. Or you can just write a Perl script that runs the same query against each server. Optimizations. So we added a bunch of optimizations in 5.0. One of them is a engine condition pushdown option, which when you do a select on an unindexed field, so when you're querying an unindexed field, we can then evaluate that condition inside the data nodes instead of the MySQL server node. So instead of doing a full table scan over the wire, we'll push it down to the data nodes, and if the data is fragmented across, you end up having these conditions evaluated in parallel. So you can actually have these unindexed table scans happen in parallel on separate machines, and then just ship over the wire your result set and combine them, which gets a big performance improvement there. And we say it's common to see about 5% speed improvement over 4.1 without this feature. And you get the details of this, sorry, I pressed the wrong button, in the explain output. So it can say what conditions it's pushing down to the data nodes. And this can be arbitrary nestings of and, if, not, in, all these kind of things. Because we actually have inside the data nodes a whole bunch of expression evaluation language. We compile it into that inside the MySQL server and send it off. In 5.0, we also integrate with the query cache. So you can use the query cache to cache queries that are querying cluster tables. So that works well. We also do batch lookups as well. So when you do select star from T1, where primary key is in a whole range of list, instead of asking the data nodes, what's primary key 1, 2, or 3, we'll just grab those in one chunk and send them down in one query. And you get batched lookup, which gets about 2 to 3 performance gain over what we had in 4.1. Sorry if I'm going through quickly. I've got a whole about half hour of extra stuff after I finish these next 2 slides. So, schema considerations. Internally, all tables have a primary key. And if you don't set one explicitly, what we do is create a hidden one. And you can do some real cool tricks with partitioning in 5.1 to get table partitioning across nodes based on things other than the primary key. We have 3 types of indexes. We have primary hash indexes, we have unique hash indexes, and we have ordered tree indexes. And naturally, we've implemented these in a way in 4.1 and 5.0 that optimize this for a main memory implementation, so that you don't store your entire key in the index as well. We just have a pointer, which is a lot more efficient for main memory, because it's costly on disk, but main memory it's cheap to look up a pointer. And you can create a unique index only using a hash index. So if you're not doing ordered stuff and just doing key lookups, you don't need to waste that extra memory and time whenever you do updates. And the primary key is a primary hash index and an ordered index, unless using hash is specified. So we give flexibility there. I wrote this script called ndbsize.pl, which goes through an existing database and works out how much space it's going to use in various releases of cluster, and says, you will need this much memory kind of deal to do that, as well as it queries the actual number of rows you have. So that's a little utility to say, will my data set reasonably fit in cluster, and which version do I have to look at due to space-saving optimizations we've made in 5.1. Right in the middle of the talk, I shall give where you can go to find out more. Our online documentation is ever improving for cluster. We have a web-based forum for those people who can't use an email client, and we have an email-based thing, and us developers do hang out there and ask and answer questions and stuff. And there's getting more people out in the community as well. Recently released was a book on MySQL Cluster, which we've got some good feedback on. 2 of the guys wrote that. Basically, someone came up to us and said, there's a bunch of stuff I had to find out myself. This book has a lot of those things. And you can also send me an email. On to part 2. It is. Yep. Cool. So what happens during node failure? So node failure and node recovery. Nice bit of technical stuff here. So we have a very simple cluster here with one node group and 2 nodes in it. So number of replicas equals 2 nodes. Node 1 melts. Have you any idea how cool it is to find a picture of a computer that melts? And we go, well, we detect the node failure, and so we grab fragment 1, so the fragment of the table from node 2, because this has 2 fragments here. Node 2 will take over being the primary copy of that fragment, which is just like some internal stuff of who takes charge of some of the protocols. So we do node recovery there and start processing transactions really quite quickly. Just depends how long you can configure, like distance between heartbeats and stuff, to how quickly node detection can happen. So assume you now replace node 1, for example, grab a new machine off the shelf and plug it in and start the storage node process. And node 1 will then just copy fragment 1, fragment 2, so all the data it should have off node 2. And the rate at which it does that is configurable. So you can then work out how long my nodes are going to take to recover and how much network bandwidth are they going to use up while doing that. So you can limit the impact that node recovery has on the cluster, which is, good. Yeah, question? How do we determine when a node fails?
Because if it's not hard down, let's say the machine has bad memory, and now it's serving bad blocks, and they don't agree with the router. Do you do some kind of comparing that with the other nodes and deciding, oh, that one's serving bad data, I'm just going to mark it bad?
Okay, so the question is pretty much, how do we detect that a node has failed? Like, do we do checks for, like, if the node's serving up bad data? We have, like, a bunch of check summing stuff internally, and we have a lot of asserts scattered throughout the code that, like, checks for sanity of various things. And when we discover that a node's doing something bad, we shut it down. Like, we have a lot of stuff in there. We'd much rather have the node go down or, worst case, the cluster, than start serving up bad data. We're really into that, which is, interesting when you go to, go use code for something it wasn't really originally designed to. You have to realize, well, that condition has changed now. We have, lots of strict checks in there. You can also add extra checks for doing extra checksums on the stuff going across the wire. And that's along with the heartbeat protocol we have to actually check that the process on the machine is responding. And you can also, then its view also happens of the other heartbeats on the other nodes. So if it just gets unplugged from the network, it will say, well, I can't see anyone. I can't see enough nodes to form a cluster, and it shuts down. So we have a lot of internal checks on stuff like that. So we pull the F1 and F2, so the 2 fragments, over the wire at a limit as which you've configured. And we then, node 2 will no longer be the primary replica for that one, and node 1 takes over and starts processing queries again when that's done doing node recovery. Part 3. Better than Star Wars yet? No one's as bitter as I am, I see. Cool. Episode 3. I have a transition on that slide. Did you know that? I didn't. So, new in 5.1. In 4.1, cluster was the new thing on there. We started the integration to have MySQL talk to the cluster nodes in the most optimized way. In 5.0, we added engine condition pushdown, which I've mentioned before, of pushing where clauses on unindexed fields down into the data nodes. And so when you have your tables fragmented across, so multiple node groups, you can do stuff in parallel and get cool optimizations that way. We have batch read interface, so we send down the where in 1, 2, 3, 4 down to the storage nodes in one go, reducing the number of network hops because latency is a real killer in these apps, which is why SCIs are something to look at, like faster transporter layers and stuff. 10 gig E buys you basically no latency benefit over gig E. You get big bandwidth, but latency is where your queries take longer. We have more metadata objects, so we support more number of tables in the cluster, that kind of thing. We use less index memory in 5.1. We made a bunch of optimizations in that. sorry, in 5.0. Enable query cache, so we use the query cache and cluster. They work together nicely. And today I'm talking about what's new in 5.1. This is very similar to the talk I gave at the users conference, like really, really similar. We do variable sized rows. So in 4.1 and 5.0, no matter how much you stored in like a varchar column, for instance, we still allocated the same amount of space, which provides some nice deterministic things of how much data is going to have and all that things. But a lot of people whinge about this giant chunk of wasted space. So we took that thing and just chopped it off. So we now support variable-sized rows, or variable-sized attributes, which is the internal term, on rows in 5.1. So the space saving is pretty obvious, especially when you consider rows and fields that are stored in main memory. So instead of having all this wasted space, you suddenly pack all these rows together and you get a lot more inside your RAM budget. And we naturally just use as much space as needed around the place. So you're using a lot less memory. My NDB size PL script there knows a bit about that, so you really will see the space saving of taking your data to 5.1. So we do variable size rows. We pack more rows in per gigabyte of memory, which means we can store larger data sets, which everybody loves. So we also added in 5.1. 5.1, I should mention, is currently in beta and will later be stable when it's ready. And you can play weird formulas and to when that will be the case. So online add drop index. So as people probably know, that when you want to do like even an alter table or an add an index to a table in MySQL, we create a temporary copy of the table that looks exactly how we want our table to be. And then with a lock held, we like copy every single row and do inserts, inserts, inserts until it's filled. We then delete the old table and rename the temporary table. Now this one, it works. It's universal, no special storage engine implementation, but it uses twice as much memory. You hold a lock for a while and you're copying a lot of stuff around. With Cluster, this is really expensive because you're no longer reading stuff off disk and writing it to disk. You're pulling it across the wire and then sending it across the wire, which, who thinks that's going to perform well? Yeah, nobody. So what we do in 5.1 is we add an index on top of the existing table and then just fill it up in the background, or you can still run stuff against it, and you have an index on your table without copying all your rows across, without using twice as much memory, just constructing it on the fly. Yeah, and don't worry about is this all new code and stuff. Like this build index code has been tested for a long time. It's like the existing stuff. And to drop it, we do the same thing. We just take that index offline and get rid of it. So how much faster is this really going to be? I now present the world's worst benchmark, which is running an entire cluster on my laptop with other processors, like with Evolution open, so there wasn't much RAM available. There's 2 gig in there. Evolution developers. So in 5.0, let's say, create an index on T1 on B. It's going to take so much time. Ignore the actual time here per number of rows. But on the same machine, in the same configuration, not changing anything else I was running, you suddenly run that in 5.1, and it supports online index generation. So that really time there is just, you'll have time to make sure the metadata stuff is synced across machines, that kind of thing, across the nodes. And building the table is pretty quick. And you'll notice that here we say how many rows have been affected. So every row in the table has been affected by building this index, because it's every row has this. But in 5.1, we don't actually affect any rows. We just affect creating the index. So you can have online add drop index, which does it faster in 5.1. Naturally online has a whole lot less memory requirements, as well as being able to have a more adaptive cluster, because you can add and drop indexes as you need them. We also have user-defined partitioning. So as I've mentioned before, you can have your data set split up across multiple nodes and have copies of this. So currently what we do, since the dawn of time, is you have a table inside cluster with a primary key, and you have a bunch of data nodes you're going to store data on, just split up into your node groups, so each holds half the database. We apply a hash function, and we then work out from that where we're going to store them. So you get a roughly even distribution of rows going to each node group. So you have this perception of one great big table, so you select and get it all in one, and the reality is behind the fact it's spread across machines, and it just sort of magically assembles them back when you do select in the right order. So here we can say we have two partitions. And the default in the 5.1 syntax for doing partitioning looks a bit like this. We have partition by key, because we're partitioning by key. We're using the default way of doing keys. The first partition is in node group 0, and the second partition is in node group 1. So you can actually now like create tables that are only partitioned on a subset of your data nodes and do like a whole bunch of really stuff that makes you have to think about your data set. But in 5.1, we can do user-defined partitioning. So instead of having this automatic thing that happens in the background, you as a user via SQL can type in where you want things partitioned. So you can partition by key, which means you can either put in your own key specifiers in there and your own node groups depending on where you want different tables to go. By range, we say future for cluster. We may not end up supporting this as a supported feature in 5.1. These decisions are the ones that are currently being made. So if you really, really want this, pipe up now. So you can partition by range, which you can do this on any table type in 5.1, but we're just sort of working out whether this is going to be something we're going to actually support with cluster. But you can partition by range to say partition 0 has values less than 10,000, and all those are stored in node group 0. And another range, just like less than 100,000, is in node group 1. So if you have your own idea about better ways to split data up across node groups, you can do it that way. Or to try and balance some load or do something weird like that. So, or by list, which again is possibly in the future for cluster. So you can then give a list of values. For example, here you have like country numbers, or sorry, city numbers, and you can say anything with those goes node group 0, node group 1, that kind of thing. So user-defined partitioning gives the user control over the physical distribution of data. So you no longer like accept our hash function, which works really well with 2 to the n nodes due to the linear hash stuff we're doing. But if you're doing like like that, like 6 nodes, you can get a little bit like 6 nodes, 2 replicas. It can get a little bit non-evenly spread. So you can help do better for that if that's the situation you want. But we also support this cool thing called MySQL Cluster Replication. We're not talking about the internal mirroring of data between nodes here. So not that nodes in a node group, number of replicas thing. We're talking about taking data in one cluster and replicating it to another cluster over a normal MySQL replication channel. So why would you want to do this? It's actually the usual reasons that you would use normal MySQL replication. You want geographical redundancy in case the data center goes away, for example, and you get blue lights in your eyes. That's a feature. You can get select blue lights. You can also split the processing node across the clusters. So when you want to do like, just say monthly, weekly reports and stuff like that, you can do that all in the slave cluster and not interfering with what you really want, this HA cluster there that has to process those transactions by priority. So monthly reports is a good example of that. So a quick overview of MySQL replication, which probably most people are familiar with already. You have a server, you run queries against it, insert stuff there. These queries go to a binary log on disk. You have a slave that sucks these queries over the wire into a relay log, and it goes through this log, runs the queries, and executes it on itself, as well as it can write out to another binary log, so you can chain your replication slaves. And as you do new queries on the master, these are asynchronously traveled across and applied to the slave. So it's asynchronous replication. So you can have a structure something like this. We have a master that writes a binary log, and you have a bunch of slaves that read from this master that also do a binary log, and you have slaves sitting off those slaves that also apply all the database transactions. Then you can have some slow, unreliable network in the middle with a bunch of slaves on the other side of it. And if this slow and unreliable network goes away for a little while, for example, your ISP decides to remove the internet connection from a data center, and it comes back up, it will then easily, these slaves will catch up. They'll just keep applying things, reconnect, and reapply. And you could also still run some select queries against them. So back at cluster. We've got a bunch of data nodes here in the cluster and a bunch of MySQLDs accessing them. You can also have, as I've mentioned, a C++ API we call the NDB API doing stuff to the cluster as well. So you have SQL coming in from the MySQL nodes, like update statements, insert, update, delete, anything that changes data. And you can have like function calls inside the NDB API nodes. So So this isn't SQL, the C++ API. It is, perform a table scan on this table, with these conditions, all that kind of stuff. And the MySQL server is, in fact, talking to the cluster through the same API. So if you think in a traditional replication role, these MySQL servers would be writing a binary log of the queries coming in, like insert, update, delete. But how are we going to get the modifications made by these NDB API nodes into these binary logs? And more so, how are we going to ever apply these logs on a slave? That is, we have no real communication between the MySQL servers to say, for example, this query was run first and then this one. So what order would we apply these in? The serialization of the queries is done inside the data nodes. So the MySQL servers don't know about that. It's all done inside the data nodes. So what we really need to have coming out of here is a single canonical binary log that gets all the updates being performed anywhere and gets these from the data nodes from where the serialization happens. So when you get this binary log and apply it on a slave, you actually get the same data. It's like this thing that people like we hear. So we have this new thread inside the MySQL server, which we call the NDB Injector Thread. And what this does is it subscribes to events inside the cluster. So NDB is the short word for NDB cluster, which is the storage engine MySQL cluster. You know, that Unix thing, shorten everything to 4 letters or less, NDB cluster. So we subscribe to events, and an event can be row was committed, and it sends across a row of this row was committed to this table with the row data there. So we're using row-based replication here. We inject that row into the binary log. So we can grab what rows are committed in the cluster and inject it into the MySQL binary log. So we get this single binary log that is a canonical representation of what's going on in the cluster. So it's not just one MySQL server there. You get the binary log for the entire cluster, including any NDB API applications that could be updating it. So it looks something like this. You have a master box here, which grabs all the updates happening here and writes them into a binary log. So if we have a closer look at how this works, we have a master cluster here. So we have a cluster here where we've got a MySQL server that's going to act as our replication master. And applications could also query this, but more commonly you'll have them querying other nodes, so you have as much load spared for this machine as possible. You can also have NDB API programs coming in here or other MySQL servers. And the NDB cluster handler inside that is where the injector thread lives, which will get the events out of the cluster and write them to the binary log. You can then have a slave, which can also be connected to a cluster. So you can have a slave cluster, or if you're feeling adventurous and think that one of the other table handlers can keep up, you can quite welcomely have like another one there. But we're going to go with the cluster because that's what real customers are using and what we envision most people will be using this for. So there's a replication channel between these two, which is the same normal replication channel used between MySQL servers. So it's using all that existing code, and it's just using row-based events like inside the binary log, which you can also use for other table types. You have an IO thread in the slave that pulls things into the relay bin log, and then an apply thread that you asynchronously pull this across, and you have the apply thread apply these row events inside your slave cluster. And this cluster could also write a binary log as well. You could also have machines writing binary logs out of that and chain them. So if your master cluster goes away, you can still run applications against the slave and do some manual failover like you do now with, say, your master went away and your application set up. You can promote one of the slaves. So you can do it the same way, except now there's just clusters attached underneath instead of a single box. So who spotted a single point of failure in this setup? Yeah? Where are the bin logs stored? Yep. So we only have like one master here and one slave here and one replication channel. You can also have another machine attached to the cluster also producing a binary log. And you can have another slave standing by to apply things if this slave goes down. And you can also have a redundant replication channel, like, for example, a different provider's internet link. So if the master goes away or the replication channel goes away, you can do failover, so you can type in the commands to do failover, and have this backup replication channel down here take over replicating from the master cluster to the slave cluster. So I think this is really cool. For now you have like lots and lots of redundancy. And it's not just cool, I call it shiny. So how do you make this failover happen? Anyone else get I was a Firefly fan? Shiny, right? Okay. Everyone should watch Firefly. So how do I make failover happen? So first I'll explain a bit of a concept inside cluster. So we have this idea of an epoch, which is a point of synchronization in the cluster. This is the checkpoints I was talking about before. Everybody agrees, so all the storage node agrees about what transactions are disk persistent. So in the case of total system failure, what would we all restore to? So in case of a system crash, that's where we recover to. That's what we call about epoch. Really simple explanation of it. So back to failover. It's a currently manual process, like the same you do with normal replication, promoting a slave to a master, but it's only 4 simple steps for cluster. These are also documented in the manual, so don't like furiously write these down. So the step 1 is to find out where the slave cluster is up to. So in the binary log produced by the injector thread, each global checkpoint, so each epoch happening in the master cluster is a single transaction. So we end up having the same disk persistent recovery thing in the binary log as well. And where we are up to in applying this is recorded in the slave. So we've added a new system database called cluster, and we have a table in there called apply status, which is 2 columns, server ID and epoch. It is also engine equals NDB, so it's available anywhere. So you can check from any MySQL server connected to the cluster what epoch it's up to applying. So on our backup slave, so on our backup cluster, our backup slave, we get the maximum epochs, the latest epoch that we've applied. We then go to step 2. We want to find the binary log position for this epoch. Since you have multiple servers being able to produce a binary log from the master side, you can end up having like purging bin logs at different times, or even like bringing them up to produce a bin log at a different time. So the position in the binary log, like the binary log file number and position, can be different for epochs on different machines. So we have a bin log index table, which maps bin log position to the global checkpoint, which is the epoch. And it also has a bit of statistics there of how many inserts, updates, deletes, and schema operations were per epoch. It's my ISM table, which is per master. So each master has the different mapping, as I mentioned. So we grab the latest one epoch we've got from the slave, and then we want to, on the backup master, select where is this epoch in our binary log. Step 3, we want to synchronize the backup replication channel. So we want to run the change master query. So on our backup slave, we use the information we've gotten from the previous queries and go change master to blah and hit enter. And the 4th step is the simplest step of all. You say start slave. And then it starts replicating from where it left off. And we'll hopefully catch up in time. You have blow up animals work through here often? I work from home. Sometimes this weird stuff just doesn't happen. In fact, probably more weird stuff happens, but I'll be sure to get the company to hire someone to walk through with blow up animals. So, a couple of limitations in the current implementation. The failover of the replication channels is a manual thing, so you have to type in those things. So we haven't automated promoting slaves to masters. That's naturally, as you can appreciate, a tricky problem. If you have a solution, we'll listen. But you can script like this changing over of it, so you just have to have someone type in to run the script. And since all the updates are going through only one injector thread on one node, there is actually a limit to how much transactions you can have executing on your cluster and go through this replication channel as it is now. So we say this is generally less than what you can achieve with a decent sized cluster and hammering it, which is a shame, but not everyone is running 100,000 update queries a second or something like that. So we're working on overcoming this as well to make sure that you can have the maximum sort of like throughput of a normal cluster and replicate that. But you can now have this very high uptime cluster, so we say 5 nines uptime, that has really good performance for a bunch of things, and we're getting like more and more performance improvements as we go. Like one of the new optimizations we want to do in the future is to help optimize joins and have arbitrary joins evaluated on the data nodes instead of up in the MySQL server. So like currently now, depending on the type of joins you're doing, you may have to rewrite those queries to have good performance on cluster. There's a bunch of tricks for that, because generally, of course, when you start doing like one table, then another, and sequentially, that's network hops, it gets a lot slower than just seeking a different part on disk. So we're working to overcome that, but a lot of optimization can be done in the query, and sometimes like denormalizing tables and a bunch of other tricks. So I think we have a cool name. NDB is cool. We have replication between it and another cluster. So you have load balancing and geographical redundancy. And we have redundant replication channels between these clusters, so you can have like internet links go down and still have replication channels happening, and otherwise known as redundancy up the wazoo. So a little bit of a quick talk on disk data. So we had two options when we were going to add the ability to store data on disk in cluster. We could either put an existing disk-based engine into the NDB kernel, or careful re-engineer NDB to support disk attributes. So we decided on number 2. For a start, this fits in a lot better with our deterministic approach to a bunch of operations inside the kernel and how we implement that. And it also allows us to do cool stuff like have some attributes on disk and some in memory and do sane transactions between them. So in 5.1, we have data on disk, and we'll have indexes on disk in the future. Naturally, you do your indexes differently if you're implementing indexes in memory or disk. So what we're going to have to do now is go have a good, solid disk-based index implementation as well as supporting indexes in memory. So you get a lot of options here. So a few concepts. You're probably familiar with in NoDB tablespaces. We have things a little bit different in cluster now in 5.1. A tablespace contains several data files, and you can add these as online operations. You can also have another tablespace and have different data files in it, you can split things up across spindles on different RAID devices, that kind of things. And you also have a log file group, which is used for recovery. You can have undo files in this and naturally add them as well. Current limitation in 5.1 is we only have one log file group. In the future, we'll have it so you can have multiple log file groups, and so you can have tables in that table space on that spindle with that log file group on a different spindle, and another table space, another log file group on different spindles, and do way too much stuff for DBAs to tinker with. And files are per node. Because we have replicas of things, and we split things up, partition them, you have these files on each node. So let's look at the SQL. Creating a log file group, pretty simple SQL. Give it a name, add an undo file, the initial size, as well as engine equals NDB. You can also add another one, pretty simply, alter log file group. We also don't currently auto-extend files, but you can always add more files to it. And we do plan to have auto-extend in there in a future release. Tablespace, the same thing. Very similar, create tablespace, give it a name, a data file, how big you want it, engine equals NDB. You can also add stuff to it as well. And we also don't auto-extend these. So how do you create a table that stores things on disk? So if we create a table here, we have a primary key and 2 unindexed columns. We also say which tablespace we want to store it on. We say storage disk, so it's going on to disk. B and C columns here will be stored on disk, and the primary key 1, so P key 1, will be in memory as it's an indexed column. If you alter table to add an index, those fields are going to have to be moved to main memory as well. So to check free space in there, we implemented a new information schema table. So instead of doing show status or doing a bunch of other things to try and find out how much space is being used by what in your data file, you can now go select from information schema.files. So information schema in 5.0, we've extended it in 5.1 to be able to query files. So there's a bit of an ongoing debate whether we're going to keep this inside the information schema database or if we're going to move it to a performance schema, so where you put more performance metrics inside the server, have a separate schema to query that. So you have this nice separation between DDL changing stuff and stuff that actually happens to the queries. It's a lovely design thing we get to debate out. The actual schema of the table is pretty decided and supports every possible way you could put data in files. So for any storage engine that comes along, you can actually reasonably put rows into the information schema table. It currently only has information about NDB tables, but you can pressure your favorite storage engine developer to add the code required to their handler. And you do need, of course, to understand the output on this table, a bit of knowledge about the internals. I'm getting the time thing, so I'm going to talk really, really quickly soon. How do we allocate disk space for cluster? We have a data file, and we split this into extents. An extent is simply a unit of allocation of disk space for cluster. So when you create a table and store some rows in it, we allocate an extent from the data file to that table and start storing rows inside it. And each table is allocated extents. So when you create another table, it gets a separate extent, which gives it a room to have contiguous rows on disk. So as you fill up the table and get the extent to be full for that thing, you need another one. So table gets bigger, we allocate another extent on disk. So in this situation, we have one full extent, one partially used, and if you delete rows from this one up here, we don't actually like reclaim that yet. We probably will in a future release. But you can get that and it'll still be used for that table. So if you like delete rows in the middle, we will reuse that space. And here we have one free extent. So if we create T3, we can allocate one extent to it. Or T2 can grow by one extent. Or T1, that one too. So information schema files for data files. We have a data file, what table space it belongs to, what the size of the extent size is, the number of extents in the file, and the number of free extents. So the free extents multiplied by the extent size equals the free bytes that can be allocated to tables. So this we're not reporting here the free space inside the extents allocated to the table. We're saying how much extents can be added to any tables. You can use like useful views, like to get like a df-like output. So we have nothing. We create a table space. You can see now that we have data files in there with 100% free space. And when you create a table in there and insert some rows, you can then see that the space goes down. So you can just monitor this to work out when you're going to have to add more data files to the cluster. For log space, we also have some stuff in there. And if you're running out too often, you're getting too low log pressure, you may want to add some more. So the future of, perhaps we will report an approximation or even exact count. Approximation's a lot easier for us to do an approximation of free space inside the extents, and of course, other storage engines. So, internal stuff. Of course, we now need a buffer manager. Since stuff is on disk and we have to cache that in memory, you have to work out that caching strategy. So, a good buffer manager equals good performance. Our one is okay in this 5.1 release, and naturally we're going to optimize that as releases go on. We use a no-steal algorithm, which is the same we've used for a normal cluster. That is when you say the maximum transaction size, the maximum operations that can be affected. So you have this like deterministic quality of how many things can be going on at once and how much memory you can allocate, which is the same as always and configurable. And also saves some disk writes, which is nice. We've also added optimized node recovery. So traditional node recovery that I talked about before copies everything over the wire, which isn't too bad for a main memory database because a couple of gigs over a wire isn't too bad. The advantage of this was, of course, easy to implement and get correctly. Not too bad for a few gigs of data. Of course, the bad side is it's very, very bad for disk data when you suddenly have, a lot more data having to be copied over the wire. So there's a paper out there for the actual algorithm stuff and stuff we considered. And basically what we do now is we can recover from checkpoints. So copy over a delta across the wire instead of the entire data set, which gets to be quite neat and saving time. And this also works for main memory tables. But naturally, if the disk died in the node, you're going to have to copy everything across. So disk data lets you get more data inside cluster while keeping main memory performance when needed. So you can create some tables in memory, like with some fields in memory and some on disk. So depending on the kind of workload and transaction load you have on them. And any questions? Do we have multi-versioning? Okay. We do not do repeatable read, but we do not we're a transactional engine. So we have transactions, but not repeatable read. Repeatable read gets really tricky when you want to do it deterministically. So it's actually a tricky problem to solve inside how we've got things there. But if someone really, really wants repeatable read, we'll work out a way to do it. Any other questions? Okay, I have one little thing to go over. In 4.1 and 5.0, we've done table auto discovery. So when you create table like schema ops on one thing, we discover that in all the other MySQL server nodes. So you don't have to write create table on every MySQL server. But if you did create database, you had to do that everywhere because we didn't auto discover databases. But if you're using 5.1, you create database and have replication on, they get detected everywhere, which is just a bit of a UI nicety. So we have table auto discovery now, and 5.1, database and table 1, as well as all these lovely features which I've talked about, and the increasing efforts to do better error reporting, more internal QA on the 5.1 release than we've ever had. So there's been lots and lots of bugs found internally, which means we have to fix them. Improvements in cluster management. Can you tell we're in a bug fixing cycle at the moment? Improvements in cluster management, like restarting multiple nodes at once and other such things. Improving documentation, so the documentation's in a lot better state than it was like a year and a half ago, as well as improving the ease of use of configuring the cluster. And I was told by our support people I have to add in that we have total kick-ass support. So we have pretty intense level support for this kind of stuff. So thank you.